It's unfortunate that Chris has been here for these past couple of weeks.
What?
It's unfortunate Chris has not been here these past couple of weeks.
Oh, yeah, that's true. That's true. But anyway, like, I hope he will come on the next call and spend more time with us. So yeah, Chris, we are waiting for you. Anyways, I hope he is following the recordings. Let me share my screen. Need to close this and open book. And probably not the book itself. Yeah, I just misclicked. I wanted to open this. So I kind of put everything into kind of notes here. So instead of Untitled 7, I can say that it's like a grand picture or something. Grand scheme picture of theoretical physics. It sounds pretty, how to say, provocative in some sense. It's not that, I guess, but like overall. And in some sense, it just describes, you hear me, right, guys?
Yeah.
Yeah, okay, great. So in some sense, it just describes the plan of, or like contents in some sense, of the Physics from Symmetry book by Jacob Schwichtenberg. So I guess that's the picture that this book actually gives you. But like in some sense, that's exactly the theme I was lacking. Like to put standard model, QFT, quantum mechanics, gauge stuff, fiber bundles, etc., like into one bigger picture. I guess like that was a problematic point for me because it was so confusing. Like you have in QFT, but you also have the standard model, and it seems that standard model is using QFT, but how they are exactly connected, like how one comes from another, or how they are related. Like in some sense, I guess that this grand picture gives you like a good foundation to move on, or like understanding on how to approach learning the theoretical physics overall, in some sense, of course. And like when having that foundation, you can move on probably to books like Penrose's Road to Reality and any other stuff, because you'll be able to put more and more information on the skeleton and like build like your understanding from like starting from that. Like and probably some books and maybe some latest researches, maybe it will ruin that picture. I mean, for example, you see like number one I have here Spacetime, but like maybe work done by Nimark and Nihamet will say that spacetime is not that crucial. Like maybe we can ruin the spacetime idea and like move away from the spacetime. So maybe it will transform the picture. But nevertheless, so yeah, how the book starts. Book starts from the spacetime actually, and the symmetries of the spacetime, the Lorentz group, and reducible representations of the Lorentz group. So and this gives us scalars, spinors, vectors, etc. Like I mean Maxwell fields. And stuff, and like by adding translations to it, or in other words, isometries, we are getting to the Poincare group, and inside the Poincare group, we can see like that we are having like two Casimir operators to basically label the representations or label the particles. So we have mass operators there and Paul Lubansky spin operator, and we are getting two foundational labels for each particle, its mass and its spin. So that's how the book starts actually. And in the next chapters, Jacob talks about variational calculus, principle of the least action, and from that we can have our Lagrangians or Lagrangian densities actually. He also talks about particles, particle versus field theories. So you know that, for example, like quantum mechanics is a particle theory. So we kind of starting with a system of some fixed number of particles, and that number kind of cannot change. But in field theories, we have the particles being annihilated, some particles being created. So we have a dynamical system described like in a more flexible way in terms of like basically changing the number of particles in the system. And also he considers Noether theorem, so which actually talks about symmetries, giving us the Noether currents or conserved quantities from the symmetries. So I guess I can even put here like the quality sign instead of just being one arrow. Yeah, and like starting from these two big themes, like spacetime and its symmetries, variational calculus and conserved quantities in there, and Lagrangians, by combining them, we could we can come up with the correct Lagrangians for the free theory. Of course, there is some magic to it happening in here, and I bet that Chris won't like that magic because it looks like some voodoo stuff happening in some sense. But to sum up it quickly, it considers just two main ideas. Like we need our Lagrangians or Lagrangian densities to be Lorentz invariant, and we need to avoid Ostrogradsky instabilities there. So, and these two restrictions, they actually give us free theory Lagrangians. And the free theory Lagrangians, they, after solving the earlier Lagrange equations, will give us the dynamics, the correct dynamics of the fields. So we will obtain Klein-Gordon equation, Dirac equation, and Proca equation, Proca. So, yeah, and they will describe the corresponding scalar, spinor, and vector fields evolutions for us. So that's kind of the base, and like the first probably half of the book is talking about that stuff. And after that, we can come up also with like internal symmetries of these free theory Lagrangians. So we can notice that there is some kind of redundancy in these Lagrangians mathematically, which is kind of symmetric, I may say. So I kind of marked it by U1, SU2, and SU3 groups here. So with U1, we kind of be acting on the singlets, so on scalars. SU2 will act on the doublets, like 2D vectors, like spinors in this case, and SU3 on like 3D vectors, like C3 elements, so it's called triplets. And internal symmetries, they come up from like free theory Lagrangians, but to get... Yeah.
What is C3 elements?
C3, like, I mean, complex plane tensor 3 times.
Okay.
Right? 3 complex numbers, that's it.
Okay.
Yeah. And in this case, I'm talking mostly just about like having like 3 fields. So these triplets will be about quarks actually. So you will need 3 quarks. One moment.
Yeah, that was my actual question. What corresponds to physical reality?
Я не поїду. Я буду тут. Давайте, пока. Yeah, sorry. My wife just wanted to tell me that they are going to the beach, so. And I'm staying here. What you said, Alex?
No, you basically answered my question. I misspoke. I wanted to know what kind of particle or physical thing it corresponded to, and you answered that really.
Oh, okay. So like we will talk about all of that stuff later in more details. So I'm kind of just talking about global view of everything. Of course, you also need to talk here about global versus local symmetries, and it's a really big talk. So in some sense, everything here, or number 4, could also be named instead just internal symmetries. It's the same as to say like gauge. So it's like gauge theories in some sense, yeah, or gauge symmetries. So yeah, and external symmetries, they come from the spacetime symmetries and Lagrangians. They also are of the 2 types actually, because there is 2 type of Poincare group symmetries actually here. Like one type is infinite dimensional one, so we have infinite dimensional representations, and we also have finite dimensional. And like one, like this, they will the infinite dimensionals, they will correspond to the basically mixing up of the coordinates, like x mu, I may say, like where mu is just like some index of from 0 to 3 or like from 1 to 4, like 4 vectors, and they will act as derivatives actually, like something like d mu, which corresponds, or maybe I d mu, which will correspond to the momentum, like p mu. Or, for example, what else? Like the rotational operators, I mean, like orbital momentum and that stuff. So it will be something like x nu d mu minus x mu d nu, something like that. And finite reps of the Poincare group, they will be similar to the same stuff we were seeing. I mean, we'll have like SU2 representations, for example. and I mean SU2 by SU2 actually, and they will just mix up the fields components. So if you have like fields, some phi capital with some indices here, I don't know, like phi probably, then it will mix up the field components overall. Yeah, so after adding the stuff to, or like paying our attention to the internal symmetries, we will find out that there is no invariance for the local internal symmetries. So we have global symmetries for the free theories, but there is no invariance for free Lagrangians for the local gauge symmetries. So like people just noticed that by using interactions, and for electromagnetism and QED, it means using for potential, A mu. It means that like if you will use it, we can get the local symmetry. And I just mark it by covariant derivative. So in some sense, it just means that we are using something like d mu minus like I q A mu. Like, so this is a connection, and this is the covariant derivative in this case. Yeah, and by using that, we are obtaining interaction theories, Lagrangians. Maybe I should have written here something like ITL, if I already marked an abbreviated free ones. So we will get like 3 theories for these, right? QED, QCD, and electroweak theory. And for electroweak, we will also have Higgs mechanism. We also will need to use the chirality projectors here to make sure that weak force interacts only with left-handed particles for fermions. And like we need to assign the mass for the quarks and for the fermions. So we are introducing Higgs mechanism and spontaneous symmetry breaking to introduce these mass terms to the Lagrangians. And we also obtaining the new charges from that. So we are getting electric charge, isospin, and color. So basically we are getting 3 more labels to label our fermions, our particles here. Yeah, and bosons also, of course. What I left here, some note. What about the mass terms for quarks? Are they included twice? Let's not talk about that right now. I don't want to go to the side, but anyways. Yeah, so let me look if I have said anything more. So yeah, like if you combine all of the interaction theories we got, we kind of get in the whole, I guess. Maybe not the whole, of course, but at least something similar to the standard model Lagrangian, which overall has that big U1, SU2, SU3 internal symmetry. So yeah, like that's the basic picture how to come up kind of with the standard model. We also like can leave them as is, I guess. Like I'm pretty happy with having all of these Lagrangians being separate also. I mean, it's still be working, right? We can talk about QED, QCD, weak forces, and yeah. And like, I may say that I don't understand like the whole standard model Lagrangian. I bet you have seen that big picture, right? Really big equation. There are some like Fadeev-Popov ghosts, there are some corrections for the renormalization and stuff. Like, I don't know the details of this, but at least I may say that I kind of understand like from where you can start to like grab the surface and like understand the heart of the standard model, I may say. So for me, it's just like a big Lagrangian, which gives like the Klein-Gordon Dirac equation and Proca equation as a result for different fields. And in some sense, that's how like the quantum field theory comes up. But let's first stop for a moment here. Maybe you have some questions to ask. No, you don't have any questions?
Maybe you'll have some comments. I don't understand enough to have any good comments.
So like, in some sense, you can see that like, I kind of can simplify that picture. Like I try to include a little bit more information here. But in some sense, you just start from like with the Spacetime and Lorentz group, add some bits of variational calculus, produce free theory Lagrangians as the invariants, like Lorentz invariant pieces, which could be constructed from the Lorentz group representations. And you are already obtaining like all of the possible field theories, like for scalar fields, for spinor fields, and for the vector fields. And by introducing gauge theories, you are actually obtaining the interaction theories and how like the different forces cross interact in there. Yeah, and you kind of come up with the standard model by doing that stuff. What else? What else? So, like, in some sense, QFT comes up, like, where we are getting to the QFT. So, in some sense, we have, like, free quantum field theories coming up from the free theory Lagrangians here. And, like, if we will introduce some interaction terms, then we will come up, like, with them, I guess, from the gauge theories. And, like, we will obtain other, like, non-homogeneous probably equations, having, like, some charges in them. And, like, overall, we will just be forced into that, like, into the subject of the QFT here. So, like, I may say that, like, in some sense, like 3 and 5, it's kind of using, or like if you combine kind of 3 and plus 5, you will come up with the QFT. Just like, if not saying more, I mean, if I will just stop here and just simplify the conclusion. So, like, you just need to solve the Klein-Gordon equation, for example, and you will obtain the big integral actually with the like annihilation and creation operators, like some A and A dagger in there, integrated over like K, like, right? You will have something. I don't remember the exact form, but overall you just need to solve this, and you will get something like we have seen already in quantum field theory book. Yeah, something like this, right? And then you can.
Do you have from that picture you drew later, so I can study it afterwards?
Could you repeat this?
I'm just asking if you can upload your notes or the overview that you did, so I can look at it, study it more afterwards.
Yeah, of course. Like, there is a crucial point here also a little bit missing. Like, so like from that base, from these 5 steps here, you can come up with questions like, oh, how can I get like quantum mechanics from that stuff? And like, to get quantum mechanics, for example, what do you need to do? For example, you take in like the free theory, you solve the Euler Lagrange equation, you come up with Klein-Gordon one. So you take the non-relativistic limit of the theory. It means that C goes to infinity, I guess. And with that, if you take Klein-Gordon KJ equation, it will turn itself to Schrödinger. How to write Schrödinger? Schrödinger, or something like that.
2 dots over the O.
Like that, yeah.
Yeah.
And what's interesting actually, like, that you can repeat the same stuff for the Dirac equation, and you will get what is called Pauli equation. People usually do not talk much more, like, they don't talk about Pauli equation. It's kind of in the same way Dirac equation is compatible with Klein-Gordon. So Klein-Gordon solutions, they will solve Dirac equation. In the same way, Pauli equation can be like simplified to the Schrödinger equation, I may say. But like, I don't know really much about that stuff. I was thinking about that, why I was thinking, because like Klein-Gordon, it acts actually on the scalars. So I was thinking, like, if we are obtaining Schrödinger equation, then shouldn't we consider only kind of scalar wave functions there? Like, is it okay that we are considering wave functions describing spin states? I mean, having a wave function described by the 2D vectors, for example, with spin up like being 1, 0 and spin down 0, 1. But anyways, like, it seems that we can actually. And like, that's how you can come up with quantum mechanics on one hand. Sorry, but on another hand, how you can come up with quantum mechanics like from the classical mechanics, how it was done in the Road to Reality actually. Penrose was saying, like, you know, we need to substitute the regular quantities with the differential operators. So for example, if we have had like some moment like d mu, then we should substitute it with d mu. If you have had something like, let me recall what was else. Well, of course, like if you have had like time, probably, not time, sorry, energy, it should be represented as dt. And for example, also like orbital moment in some like space coordinate, it should be also represented via that like x mu d mu or d nu. Sorry, x mu d mu, something like that. One moment, I will grab some water. Just had some cough. So yeah, like back then, these substitutions with derivatives, they look to me, on one hand, suspicious. On the other hand, like not really understandable. So that was kind of like a trick. But I guess after learning more about Lie theory, Lie groups, and representation theory, I can say that it kind of feels more understandable now, because what actually happens here is that like for the big macroscopic or like macro world, our symmetries are described with Lie groups, like translations, right? And different rotations. So like 2 points, they rotate around each other, we're getting orbital momentum and stuff. But in the micro world, what will happen to the Lie groups, right? I guess you know the answer, right? We just need to take really small actions to the Lie groups. We are obtaining Lie algebras. And that's exactly what's happening here. Like if you substitute in the values with the operators, you actually transform them to being infinitesimally small and being kind of the Lie algebra generators and elements. So that's what's actually happening. At least I think about that in this way right now, when you convert it from the classical point of view to the quantum mechanics. Yeah, what else? Also, I have a really interesting question here. Like you see, we can come up with 2 quantum mechanics equations here, like Schrödinger and Pauli. What about Proca? Like, what will happen if we will take...
I don't hear you if you're saying something.
Okay.
Really? You don't hear me?
I do.
I'll try to connect.
Yeah, please. Let's wait for Alex. Yeah, Alex, hello. Do you hear me? Alex. Hello.
Alex, are you able to hear Slava now?
Let me write to him. Maybe he will see. I even forgot that I have a sore throat for the last 3 days. So like talking for half an hour of time, it's already challenging a little bit. Like it's okay, but need to drink more. Maybe I should reconnect, I don't know. Boom. And you, Joe, you hear me, right?
I do.
Okay. Maybe I should disconnect him, I don't know. I guess I see Alex there. in the Discord.
Yeah, it says he's watching the stream.
Mm-hmm. Strange, but he doesn't respond for us, even in the chat. So it's strange. Maybe he is reloading his computer or something. Oh yeah, he disconnected. Great. That's what I was expecting. Hello, hello.
Guys.
All right, I hear you.
Yeah, I can hear you. Are you?
Yeah, we hear you. Now everything is fine.
Okay, I can hear you both now.
Great. Okay. So.
But was it on mine?
What?
What's the problem on my end? What happened?
It seems so because we were hearing each other with Joe.
All right.
Yeah,
Okay,
yeah.
I restarted the phone. Okay.
Yeah.
Good to know.
So, what you missed actually? Where you stopped hearing me?
I think what I'm seeing on the screen right now is.
I think you dropped off at the Proca when you started talking about the Proca Lagrangian.
Oh, okay. So you heard about the Lie algebras, right? Micro.
Yeah. You said that it's mostly the Lie groups.
Mm-hmm.
I think or Lie algebras it might be. That
So I was just saying that if we are coming to something infinitesimally small, we just need to go to the Lie algebras.
Yeah.
And that's how we come up with
all
all
about
these.
the derivative and using that to take it infinitely small.
Yeah. So and like with quantum mechanics, as I have said, if you take the non-relativistic limits of Klein-Gordon and Dirac, you get Schrödinger and Pauli equations. But what will happen if you take Proca equation non-relativistic limit? And the case is, like I thought that maybe that's the problem. Proca equation is describing the magnetic like four potential field, right? And like it's a vector, and vectors we are having for bosons. So basically it talks about photons, right? And because it talks about photons, and photons are traveling with the speed of light, we kind of cannot just talk about the non-relativistic limit of photons. And maybe that's why there is no like wave function for the photon. Or like a lot of physicists say that it's not possible to provide a wave function for the photon. But yeah, that's a big question. I don't know the answer actually about that stuff. And I have seen the Riemann-Zilberstein vectors being used. So the exact complex combination of electric and magnetic fields, something like that, being used to describe the photon wave functions actually. So yeah, but I'm not do not know like really much about that stuff. Anyways, so like that's how you kind of come up with quantum mechanics. You just like using non-relativistic limits. You are using Lie algebras elements like the nu stuff. So and you coming up with equations something like x with p will equal to what it should also have like something like x mu, and like if it will be p mu, it will equal to 1 basically, or like p nu it will be equal to something like mu. So you get into the non-commutative relationship between the operators in quantum mechanics. You coming up with the Heisenberg principle, and like because these new entities will be operators, you'll need them to act upon something. So you will try using some new function defined on the space, and we usually call that wave function. And when you will try to deduce its like eigenvalues and eigenfunctions and produce some kind of a like basis for that, you will learn that it kind of acts like a probability. So in some sense, you learning that stuff is talking about the probabilities. Yeah. So and you kind of come up with everything connected with quantum mechanics in this way. So yeah, I guess like overall, probably that's it. Like in talking about QFT, of course, you have similar relation between the fields and conjugate momentum, where you have like something like this instead with a Dirac delta function. Yeah, so I guess like that's it for the grand picture of things. And yeah, I guess
it was all physics, so I guess that is it really.
at least all of the conventional, all of the
Yeah,
conventional part, because you need starting from that, you can build atop a lot of stuff. I mean, grant unified theories. You can think about how to put the gravity into it. You can think more about gauge stuff. You can add strings. You can add twistors and Neimark and Nihabat stuff on top of it. And but you at least it maps everything nicely, and it's a nice place to start, I guess.
Yeah, the rest is just details.
Yeah. So yeah, that's it. I guess that's the result of learning physics for the 5 years, or how long you've been doing that? Like 5 or 4? It was COVID, I guess, when we have started, like 4 years. So, yeah.
Well, I just have to say, well done. So.
Yeah, thank you. I'm glad you liked it. Joe, what do you think about that stuff? Does it sound like good enough for you to be in true?
Yeah. This picture of theoretical physics is definitely complete. I think that one aspect of it is like imagining or like making it very clear where the holes are. You talk about adding up and including grand unified theories and things beyond the standard model. I don't think that this map needs all of those different things, right? You don't need to talk about each one of them, but maybe just pointing out like where they would go, like what the next arrow is, and put a big question mark at that next arrow.
But yeah, it depends on the actors, it depends on, like, I bet that if you will understand like everything mapped out already, you will be pretty sure about where to put that arrow, At least like right now I'm reading the article about something, like for example about gauge invariance, and I'm like, oh, okay, it goes here, like somewhere here, like about global and local symmetries, for example, and like you're studying that stuff. Yeah, or about like covariant derivatives and fiber bundles. You kind of like, oh, okay, yeah, it's also all about the gauge theory here, actually. But yeah, I mean, there are a lot of stuff to add, probably more than I can add, actually, in some sense, because like probably yesterday and today I've been watching a lot of stuff around, like reading some books, watching videos, reading articles about gauge stuff, about Wiener's theorem and stuff, about quantum mechanics. For example, I was thinking like, oh, okay, we have like a probability current, right? And we have the probability conservation. Then what is the symmetry? Like what the symmetry which gives us the probability current in quantum mechanics, for example? And the actual answer is, like, in some sense there is no symmetry, but that's the unitarity. So unitarity, and it leads to like probability currents and conservation of probability. And that unitarity, like, it was in some sense hidden because we need to say everywhere that if we are using reps, we actually using unitary reps. And that's like the part, for example, where you can go and see what like Wiener theorem is about. Yeah, so like there are a lot of stuff happening, but I was actually.
Yes. Sorry to interrupt.
Yes.
I think there is one other part of it that would be a really important thing that I'm not seeing here, and that's renormalization.
Oh, okay. Like you, of course. Like I don't know much about the renormalization. I guess that's why I haven't used it here. Like in my current knowledge and view, it should go here, like where QFT is. And so when you will start learning about the basics of QFT, and like QFT has a connection with quantum mechanics, right, via quantum harmonic oscillator. Like when you will start with QFT, understanding the creation and annihilation operators, like moving down the ladder of the, like, basically moving energy of the vacuum down or up by creating new particles, you will come up with the stuff connected with renormalization, right? As it was done in the book about QFT. But I know that for theory to be renormalized, you also need to do the correction here in the Lagrangians, right? So it's it has also this connection. So you need to have some special items added, or like terms added to the standard model Lagrangian for it to be renormalized, correct? But I
think that the very complete picture of the mathematics underlying like the standard model. And I think that to make, like, just with the title, Grand Picture of Theoretical Physics, there's there's also a good amount of like being able to make calculations that predict things. Like for example, how to calculate amplitudes. There's scattering rates, things like that. Like which is still kind of in this realm of theoretical physics. I guess you could call it phenomenology, but that is like where you draw the interface. And so as part of the grand picture of theoretical physics, you have to like include that interface with experiment, because all of this is a theory that builds up, and then you build a bridge over to experiment so that you can have data pass between the two.
Yeah, that's true. Like for me, like practical tooling is mostly about like Feynman diagrams in some sense, right? And like calculating the probabilities, like S matrix. So yeah, it's like more into the QFT realm, probably. Plus also, this whole scheme also lacks cosmology, thermodynamics, right? So like some big parts are out yet, like from the grand perspective. But nevertheless, like.
Wait, does it touch upon gravity?
About what?
Did this include gravity? I assume it doesn't. Or?
Gravity also is not included here. Yes, it does not. There is no gravity.
Yeah, just to be clear.
It's more about like the particle stuff, like maybe smaller one, and just space-time. Yeah, so yeah.
Because to be super clear, the standard model doesn't include gravity. That's separate, right?
Yes. And I guess
The
like
very first thing that you have written there is space-time, though.
yes, that's true, but not a curved space-time, just a flat one. And it's funny that like gravity in some sense is the same or looks a lot like cage theories. I mean, we have similar like play of the like curvature, like pushing the objects or like masses around and masses curving the space-time, and it's very similar to how electromagnetism works, right? Where we have similar stuff, we have curvature, this one, like the Maxwell tensor, and it kind of acts similarly, and we have similar curvatures for the like the strong force and for the weak force, like some W. And probably they will be matrices. I don't remember exactly, but they should be matrices, I guess, in this case. But nevertheless, yeah, bosons, so they will live in the adjoint representations and stuff, blah, blah, blah. Nevertheless, like, it's hard to get gravity to work nicely with these guys. I guess because theories become non-renormalizable, you are getting a lot of infinities there and stuff like that. But yeah, like, I haven't read about that stuff much to this moment. Maybe we should read Penrose more one day. Probably he talks about that in Raw Reality too. And also there is like the book by Bias, that Cage, I guess it's called Cage Theories, Knots, and Gravity, something like that. And it kind of talks about the problems of getting to the quantum gravity. So yeah.
Is there any particular motivation to quantize gravity, or is it just like the thought process that we've talked about so far, where they look so similar, and you know, in QFT, when we see a nice gauge theory, we want to quantize it.
Mm-hmm.
Is there good motivation to quantize gravity?
Really, I don't know what to answer. I don't know. I'm just out of the context of gravity, actually. Like, yeah, can't say nothing yet about that stuff. Like, I heard some bits, but for example, like Hilbert action and stuff about that, like how to put gravity to the Lagrangian. And Lanczos, I guess it's called Lanczos tensor or something, like the analog of the electromagnetic potential, but for gravity. But I don't know a lot about that stuff also. I also want to understand more about local symmetries versus global symmetries, like that sector, because like in the paper about explaining gauge invariance, Jacob was actually telling that local symmetries, they are not real in some sense. So like that only the global gauge symmetries are physical, but local are redundancies. But on another hand, like what our Aronoff-Bohm experiment shows to us, doesn't it showing us that local symmetries are real? So like, yeah, there are a lot of stuff to think about actually, like a lot yet. But yeah, at least I'm happy that now I can understand, like at least accept and read more about the QFT and standard model from books like Road to Reality. Like it makes it easier by just keeping that picture in mind. And probably like instead of putting more things, maybe I can even like remove some stuff from that diagram I have here. Because in some sense it could be like some parts could be left out, and I can simplify everything just to show, like to make it more, how to say, more, it's just simpler and better to understand, because right now I have maybe too much here even. But yeah.
If you wrote this exact diagram in the 60s, like people would be blown away. Like this very dense packing of all this information. Like I think that this diagram or this table, it's a really a thorough look through these things. And sure, there are some names to maybe expand out or something, but like it's a pretty comprehensive picture here. And honestly, like this picture is not that old.
Mm-hmm.
We're talking decades or years? Or...
Probably decades.
Parts of it are a little young comparatively to the others. Like Klein-Gordon and Dirac is like the 30s, right? But then you get to like interacting local quantum field theories, and then you start talking about Feynman, and then there's like Weinberg, that was in the 60s. So I mean, they're all at least 50 years old, I guess, but some of them are younger than 100 years old.
Yeah, or so. I mean, I think about this a lot. We're so lucky to be alive this time in history, really.
Yeah. So, yeah, like on one point, I'm kind of okay with reading like physics from symmetry more, but like on another hand, I can say that like I'm kind of also ready to read more about Road to Reality. For example, like yesterday, like you kind of going into the rabbit hole here everywhere. Like on the maps, there are a lot of rabbit holes. For example, like here, like going to the quantum mechanics and coming up with the wave function. Like, what is the wave function? Like that's the question I had yesterday, and it blew my mind. Like, it's so hard to consider what is that. Like, and here we encounter like.
What do you mean? How do you mean?
I mean that.
How are you thinking about it?
I mean that, like, in some sense, you can, of course, you can take the limit, right, of the Klein-Gordon equation and come up with.
We're talking about the probability wave.
That's another story also. But like, what kind of a stuff we can put as a wave function, like in quantum mechanics? In some sense, yeah, like only like probabilistic, the stuff which behaves nicely probabilistically. So like we have all of these axioms of quantum mechanics and postulates about like wave function being a superposition of states, like with different eigenvalues, basically. Oh, sorry, I misclicked something. It should be there somewhere. Yeah, but like, for example, like if you have just the Klein-Gordon equation, you have scalar field here, right? That big phi. It's solved by the plane waves. Okay, it's solved. But then what? Blah, blah, blah. And we are getting something like, he says like that, I guess that's the solution. Yeah, that's a solution. So we have like exponential to minus int, fxt here, and phi small is that exponential. So it's like, so just an approximation. And that approximation, maybe that's exactly the non-relativistic stuff happening, right? If you are doing that m plus p squared over 2m, probably that's exactly the stuff which happens when you have like two big speeds, or like the light speed being infinite or something. I was just thinking about that phi, like what is that phi? Like I'm not sure. Like I was thinking that maybe because we are taking the limit of the Klein-Gordon, maybe we cannot put anything except scalar here, so we have scalar field, and it looks like it kind of, you see it, it is preserved here in the Schrödinger equation. So it looks like a wave function, but it's a scalar wave function. But still, we can have non-scalar wave functions, right? And that's the moment which confuses me a little bit. Like, why if we are working with Klein-Gordon and taking the limit, we can use anything else, you know? I mean, like a wave function for a spin, for example. Nevertheless, it seems to be working. Like you have different such operators, right? Like for spin, it will be just polymatrices. Yeah, like here. And wave function will be just a superposition of states, like a C2 vector. Yeah, nevertheless, like, I mean, you also can think about the stuff, like, I mean, the physical representation, like what is the wave function in real life, and there are different philosophical ways to think about quantum mechanics, right? So that's all about the how it's called, like interpretations of quantum mechanics. And like that's only one scene, like it's just a small scene popping up in quantum mechanics, like the wave function. And in QFT you still will have, of course, something similar to that, right? But it already won't be that wave function you had before. Like instead you'll have something living in like a Fock space, and kind of like something like one particle in K with K moment, one particle with K something like a hyphen, some stuff like that. But there was us, yeah. There was us. Like, and there is also a way to go from QM to QFT, right? Via that second quantization pass. I guess Chris was talking about that in the past. Nevertheless, yeah. So like there are a lot of blind spots. I mean, but before I wasn't been able to realize how, for example, QFT is connected with standard model, how gauge theory is connected with standard model, how spacetime is connected with that stuff, Lorentz invariance and stuff. So I guess like that's a really great thing that Jacob read in that book. Like it kind of gives everything to you on a plate, and you can start from there and move on.
And how do you, let's say you had this picture described before you understood these underlying concepts. Do you think it would have been useful to you to have from the beginning, or is it more like a summary of your current picture?
It's a summary of the current picture, and in some sense,
of course it is. But would this picture have been useful to you, let's say, 4 years ago?
Of course. I mean, it will be, because I won't stop reading Road to Reality. I won't stop. Like it was challenging reading Penrose's book because it was just too much to handle. Like I was feeling the time like in a dark forest, you know. So it was impossible to go. And now, like I kind of have a flashlight. Like I can move on. Like I'm ready to continue. And yeah, if I would have that in the past, I would definitely not stop. I won't stop reading Road to Reality, and I will just continue further. I will go to like ADS, CFT2 dualities and holographic stuff and twisters and like more fancy theories, but I couldn't. And also, I guess this picture is not possible without learning differential geometry, right? Like curvatures, covariant derivatives, parallel transports, stuff like that. It's impossible to understand without like knowing calculus, of course. It's impossible to understand without learning representation theory and Lie algebras and Lie groups on the like nice level. I mean, like fine enough, right? At least on the level of understanding of the concepts and some group examples like SU2, SU3. Yeah, but it's impossible. Like it's so hard without the foundations. And yeah, of course, like my way was more mathematical way. And as Joe said, the data here and that picture is not really connected nicely with the physical experiments and real life data and real life phenomena. And it would be nice to connect, like for example, the Aronoff bomb experiment and gauge theories and talking about local symmetries. So yeah, anyways, for example, like Nima, he considers that, at least he talks about gauge theory being bullshit or something. Like in some sense, I don't remember. Let me find that article.
I do remember him talking about the Higgs mechanism, saying like the world is not some crappy metal.
Yeah, like about spontaneous symmetry breaking, yeah. So if I will just put like gauge explained, oh, here is it. Demystifying gauge symmetry. So if you'll just open that paper, I actually have a video on my channel on YouTube. Like we have talked about it, about that paper in the past, actually in the detail. But now I'm seeing it with the new eyes, actually. Like it's the whole new stuff now, because I've seen the Lagrangians already. I know the symmetries already. Like I've seen how it's working, and you see that like some people, they are selling the idea of gauge symmetry. They are telling like Wilczek, like that a central pillar of the standard model is the idea of gauge symmetry, and that's true. That's totally true. But like if you take a look at the bottom of this page, you can find that Nima says, what's a misnomer called gauge symmetry, whose beauty is extolled at length in all the textbooks on the subject, is completely garbage. It's completely content-free, there is nothing to it. And it makes me like, I don't know, nervous a bit. While he's saying such bad stuff about gauge invariance. And like, yeah, people calling gauge invariance is not physical, gauge symmetries are not real symmetries. And I guess like that paper of Jacob was actually, like its main goal was to discuss such a big contrast between the opinions. Like why some physicists are talking about gauge symmetries too much and why some of them also saying some bad stuff. And it's because like probably, as far as I understood from that paper, that local symmetries are not that real in some sense. But yeah, nevertheless, even with that, I don't know about like the reality and like the connections, like when connections become real, but the picture is so similar to the gravity. So it's strange if that's not real. Like, I mean, it's still working, right? And like curvature is a physical stuff. Is like the electromagnetism is the curvature actually acting on the charges of the electric charge. An electric charge, of course, is a result, it's a real symmetry, it's a global gauge symmetry of the Lagrangian, kind of. So yeah, nevertheless. Yeah.
It feels almost like maybe they're, I don't know, it's interesting, like to this point of like being critical of gauge theories, is that it's odd to have to include additional data that is not something that like is built into the underlying structure. The fact that you have these like fiber bundles and that you have to like go above the plane of the thing that you're talking about and inject some other thing, and then not only that, but you actually have to choose the way that you inject it, like that you choose the connection. Like that's very odd when you look historically at, like, say, you know, the development of calculus or something like that. This is the first time where we've had to actually inject additional data, and the way that we inject that data is critical to the results that we get.
Yeah, but like it's interesting that if you consider local symmetries, you come up with the interactions, and you come up with the right way to describe how like photons, for example, or like electromagnetic potential, it kind of interacts with spinors and fermions, like electrons. And yeah, it's crazy that it kind of works to show you how electromagnetism works, and then weak symmetry also, and then like strong force also. So yeah, not sure about like, but yeah, like you need to go to the local theory, right, to introduce some term, like interaction term, to compensate it nicely. And like the usual argument is that like we have a special relativity, we have a finite velocity of information spreading, then like probably universe cannot have like the same coordinate prescription at every point of a space-time given to it like at the same time. So usually people are using that argument and say like, you know, like global symmetry seems like not that like good looking, and let's try using local symmetries. And then they go and like do all that stuff by adding like these terms, these gauge terms. Let me actually show one. Like if you're already talking about that stuff, right? Why not to open the corresponding page? It should be somewhere here. Interaction, yes. Charge conjugation, okay. So yeah, something like that, right? So this is the interaction term, like that small g electromagnetic potential, and then just like spinor product, which is Lorentz invariant here. And actually, like we have gamma there to be contracted with A, I guess. So it also make that term Lorentz invariant. And then we just combine Dirac Lagrangian with that term, and magically it gives us the correct theory, and it's invariant under the local symmetries. So if you substitute they don't show it here, right? Exponentials. Like if you multiply, where is it? They don't show it probably here, but the basic idea is just to multiply everything by this. So like the fermion is multiplied by exponential, where the power is dependent on the position. So it's not constant everywhere, that I or AX. Yeah, so that's it. And it produces that term with d mu AX, which doesn't cancel if you want to add the correct interaction term. Yeah, and actually you need to do a lot of more movements, right, Joe? If you will try to do the same stuff with weak force. You need to do a lot of jumping through the circles, like up, and like here we cannot introduce masses, Higgs mechanism, then that and this.
That's exactly, yeah, that's it. It's that, like, the way in which you inject all this additional data is really critical to the results that you get. I mean, it's so powerful, the results, right? We can make good predictions with this, but the whole process of getting to those good predictions, it feels very fundamentally different from other mathematical theories.
Yeah. And also, like, people haven't got there, like, right away. There were a lot of different, how to say, like, crucial results to move the theory forward, right? So, like, at first, one guy came up with the doublet stuff and tried to apply C2 transformations to that stuff. So it was, like, working, but everything was massless. And he was like, okay, I don't know how to put masses. And then some people came up with some ideas, and they've been working, like, for a decade probably to make it work finally.
I mean, maybe this is maybe I'm missing the point, but would we expect it to be a little unwieldy and complicated since we're dealing with a physical description? I mean, it's not the ideal pure math. Then you can afford to have really elegant structures, but yeah. I guess
yeah, but you know, in some sense, it looks a little bit like a brute force or something. I mean,
yeah, I was gonna say force fit before, but yeah, exactly.
You kind of try to push on the mathematics to be more consistent with the stuff you see in the experiments, right? So that's exactly what was happening. And yeah, like, it's funny that with strong force you don't have such problems, because quarks, they have the same mass. There is no problem in the color symmetry. You don't need to have symmetry breaking there.
Yeah, you know what this reminds me of? It's you both have probably seen this old picture of before we had this heliocentric perspective, where you just get a weird description if everything revolves around Earth instead of revolving around the sun. And maybe we're just thinking from the Earth perspective now, and it's really elegant when you go from that point of view, but once you go to other ones, it gets very complicated. Or yeah, I think you see the point. Maybe it's too optimized for our current perspective.
Connections are the epicycles of our age.
Yeah.
Yeah, it could be. I mean, maybe that's what Nima trying to do, like remove the epicycles. Like, let's think about stuff in another way. And also, nevertheless, like, I don't want to talk about the stuff I don't know. Yeah, but I mean, it's nice time to revisit a lot of stuff I already read, in some sense, like the Jacob paper, for example, about gauge invariance. It has a lot of stuff to think about, actually, a lot.
Well, you made a really full picture of theoretical physics, and I think that it's great. It currently strikes me as it still has the feel of, like, personal notes, so it's probably tough to share with others. But along with your explanation in this talk, I think it's a really powerful tool. And you know, as time goes on, you'll refine it further too. Yeah,
definitely. Thank you. I was glad to share. I probably like I may say that I was going there for the last 4 years. It was a long journey, you know. Yeah.
Would you have interest in writing up these notes as like a paper?
Oh, I don't know. Like in some sense, it's just copying, like you know, it's just copying the Jacob stuff. But maybe I can summarize it better, or in some sense, yes. So I don't know.
Well, I just think about like Feynman's lectures, those red books, beautiful, but they're just notes that somebody took going to lectures with Feynman.
Mm.
So I mean, that's very high standard. But I just mean, like, if you write up these notes in a nice document, it doesn't matter that they're summarizing from all sorts of places. That can be very valuable for people.
Yeah, I will think about that stuff. I guess I needed to mature a little bit more in my head, and then we'll see. Maybe in a few months. Let's read more the physics from symmetry, and then you will see. I guess. I'm eager to learn more about like physics part also. I mean, like maybe reading Atkinson book or maybe some other books. I don't know. Like there's so many books. Like there's so many books to read.
Do you mean physics phenomena or?
Yeah. I mean, like physical perspective is also like very important here, and like I also want to maybe run a little bit in the future in some sense. I mean, like maybe read V10 or string theory a little bit more. What was happening with the string theory, and like how it went off. I don't know. Like I have a lot of stuff going on in my mind. Like I mean, it's tempting to pursue different directions. A lot of different stuff is there still yet. But like I mean, it seems that a lot of stuff is like in the nearest past. It was about probably Maldacena also, like ADS-CFT, and string theory also, and the stuff Nima is doing. Like I still don't feel that I'm at the edge in some sense. Like people which are working at the edge, they doing something different in some sense, but still connected to these foundations we have discussed in the call. But nevertheless, like it would be nice to find something to put more effort or something. Like it's hard yet to for me to say it right now. Like I guess I need just to wait for some fruits to be ready on my like tree of mind. but like I'm kind of thinking about that stuff in some sense. Like I've been just watching some video about drummers recently, like why Slipknot drummer Joey Jordison was so good, and like there was a point in a video when like the guy was saying like he used pretty simple stuff, like really simple drumming patterns, but he mastered them to that level like where like ordinary drummer will give up. Like they won't say like it doesn't matter or like I don't need that stuff. And like I was thinking about physics in some similar way right now. Probably I was thinking like maybe I should find like the place, the point on that map to strike into it for a long period of time. I've been basically tapping a lot in the spinners and symmetries for the past few years, and now I guess that my inner interest leans towards the gauge stuff maybe, and maybe fiber bundles. Maybe that's because Penrose was praising them. But yeah, we'll see. I don't know yet what I will want to do in the future. Nevertheless, that's like just some high-level thoughts. Let's read physics and symmetry. Meanwhile.
Agreed. I think that was a great summary. That's all.
Yeah. I will stop the recording, I guess.